Alrighty, guys, we're going to go ahead and get started with our angled forces notes. And these notes are going to talk about the fact that sometimes forces are going to be angled and they are not going to point along just one coordinate system. So we're going to analyze specific examples where this happens. So for instance, let's say that we have a box here, all right? And this box is on a flat surface, but this box is being pulled up at an angle. So right here we have some applied force. And again, we can clearly see that this applied force is at an angle. It is not just in the x or the y. So if we were to draw our coordinate system, we would draw it with the x parallel to the ground and the y perpendicular to the ground. And we notice that, like I said, this force applied is up at an angle. So it's in a combination of the x and the y coordinate system. Fortunately for us, we remember that forces are vectors. And because they're vectors, that means that we can take an angled force and break it down into its horizontal and vertical components. So let's go ahead and draw our free body diagram acting on this box. So here's my box. I have force gravity pulling down on this box. I have force normal pointing up because it's on a flat surface. You're going to notice that I made force normal smaller than force gravity. There's a reason for that, and we'll get to it later on in the problem. Next, I'm going to go ahead and add my force applied over here, and I see it's at an angle, so I'm going to draw it at an angle. Let's say that there is no friction in this problem, so we'll just leave friction out for the moment. So if we're referencing our coordinate system, like the one from above, like I said, we're going to notice that force applied is in the x and the y direction. So we're going to have to split it up into its x and y components. So the y component is going to be the vertical part right here. So I'm going to label this as force applied in the y, or phi, and the x component is going to be the horizontal component over here. And I'm going to label this one as fax, force applied x. And then since the x and the y are perpendicular to each other, I'm going to show that by drawing my right triangle. And then I'm also going to label this angle down here as theta, because this will either be an angle that we're given in a problem or an angle that we need to figure out. And it's going to be a very, very important angle. So theta, just like we said, is the angle that the force is being applied at. So in order for us to break up this force applied into the x and y components, we're going to have to use some trig here. So let's expand our force applied triangle over here so we can really see what's going on. And we notice that we have our force applied. Then we have our force applied in the y direction. And we have our force applied in the x direction down here. We also have the angle that this is being applied at, theta. And we're going to notice that force applied is the hypotenuse. Force applied in the y direction, according to this angle, is the opposite side. And force applied in the x direction, in reference to this angle, is the adjacent side. So we're going to go ahead and use some trig to figure out what force applied in the x is. Well, since it's the adjacent side, it's going to be cosine. So we know that cosine of theta is equal to adjacent force applied in the x over hypotenuse force applied. That's going to tell us that our force applied in the x direction is just equal to force applied times cosine of theta. And let's do the same thing for the y direction now. We see that it's the opposite, so it's going to be sine. So sine of theta is equal to force applied in the y over force applied. Multiply force applied over, and we get force applied in the y is equal to force applied times sine theta. So if we were to write our net force equations now, we would see that net force in the x direction is equal to force applied x, which we know force applied x is really just force applied times cosine theta. There's no friction in our problem, so we don't have any other forces, and that's just going to be equal to mass times acceleration. The x direction is pretty easy. Let's go ahead and look at the y direction though. Net force in the y direction is going to equal the forces that point up, force normal, plus we're going to see that we also have force applied in the y pointing up. So plus force applied times sine theta minus force gravity. And that's going to equal mass times acceleration in the y direction. We know that this box is not accelerating in the y direction, so this is just going to be equal to 0. So what this really is telling us is that 0 is equal to force normal plus force applied times sine theta minus force gravity, which if we add force gravity over, that tells us that force gravity is equal to force normal plus force applied sine theta. Well, this equation is really important because it's telling us that force gravity is not just equal to force normal, which you could see up here when I drew my free body diagram. I showed you that force normal was going to be smaller than force gravity. I knew it was going to be smaller because I had an applied force pulled upwards. Since force normal and force applied y are pointed in the same direction, it's going to mean that we don't need nearly as much force normal as we normally would to offset force gravity. The reason being is that force normal and force applied y are helping each other out. Force applied y is taking some of that force off of the surface, so the surface doesn't need to push back up with so much force. Therefore, this force normal is going to be smaller than if the object was just laying flat on the surface. Because if the object was just flat on the surface with no other forces acting on it, force normal would have to balance out all of this force gravity. But because we have an applied force pulling upward on an object, it means that the force normal doesn't need to support as much of the weight of that object. Now that we looked at a force pulling up on an object, let's look at a force pushing down on an object. So let's say we have our box just like we did before, and it's resting on this surface, except this time we're pushing down on that box. So we're applying a force downward at an angle. Well, let's go ahead and draw our coordinate system that we're used to. First, we're going to go ahead and draw our coordinate system, showing that up or perpendicular from the surface is our y direction, and to the right or parallel to the surface is our x direction. Now let's draw our free body diagram of this box below. We have force gravity pointed down on the box, and then we have this applied force pointed down at an angle on this box. We also have a normal force pointed up, so I'm going to go ahead and make force normal bigger than force gravity. And there's definitely a reason for why I'm doing this, and we'll see later on in the problem what that reason is. So now that we have all of our forces labeled, let's go ahead and break up our force applied just like we did before. So I'm going to bring my force applied out here. I'm going to expand it a little bit so we can really see what's going on. So here's force applied, and in case you forgot, here's my coordinate system. Up is the y, and to the right is the x. So when you draw the components of force applied, always start with the x direction. So I'm going to start with the x over here, and the reason why I start with the x is because the x is parallel to the surface, and the angle that we're referencing is always parallel to the surface. So here's my force applied x, and then from there I'm going to draw my force applied y. I said that I was pushing down at an angle. This is the angle that I'm talking about. Because like I said, it's the angle from the horizontal. So odds are that this angle is going to be a negative number here. We're going to notice though, that regardless if this angle is negative or not, we still have the same equation for force applied y and force applied x. And we still know that force applied y is just equal to force applied times sine theta. And force applied x is still equal to force applied times cosine theta. So all of this is still the same regardless if we're pulling up or pushing down on the object. The only thing that changes though is going to be the following. So if we're looking at our net force in the x direction, So if we're doing what we did before, we're just going to say that the forces that point to the left are negative and the forces that point to the right are positive. Since there's no rightward forces here, we're going to say 0 minus the forces that point to the left. In this case, and it's just the case because we're pushing it down to the left, force applied is going to be negative here. And again, that's only because we're pushing to the left. If we were pushing down to the right, then it would be positive. But we have force applied times cosine theta. That equals mass times acceleration in the x. This is just a general example. This is not always the case. It's just negative because we're pushing to the left. So now let's take a look at our net force in the y direction. And this is the really important one. And this is really going to help us understand what's happening. So the forces that point up here are now just force normal. The forces that point down, well, we notice that force applied in the y direction is pointing down. So force applied in the y is just force applied times sine of theta minus the other force that points down, force gravity. And this equals mass times acceleration. Again, nothing new here. It's not accelerating in the y direction, so that's just 0. So that's going to tell us that 0 is equal to force normal minus force applied times sine theta minus force gravity. Well, since this is 0 over here, we're going to go ahead and add force applied times sine theta and force gravity over to the other side. And we're going to find out that force normal is equal to force gravity plus force applied times sine theta. So this means that since we're pushing down on the object, force normal is going to be a lot bigger than it normally is. And that's because force normal is the force applied by a surface, meaning the force needed to hold that object up or counteract the force of gravity. We're used to just saying the force of gravity, but really force normal is the force needed to counteract the downward forces. And in this case, we have an extra downward force pushing on this object. So force normal is going to be bigger than it usually is. And the way we figure that out is by taking force gravity and adding it to force applied times sine theta. That's how we're going to figure out our new force normal. So now we're going to go ahead and pull all of the information together that we just talked about and talk about a few more key points and then wrap this up. So let's break this down into our upward applied force. And that was up at an angle just like so. And our downward applied force. And that was down at an angle just like this. Let's look at the similarities and differences here. Well, to start off, the similarities would be the fact that force applied in the x is equal to force applied times cosine theta. That's the same for both of these. And it's the same because the angle that we're looking at is always in reference to the horizontal here. So we just need to make sure that we're taking the correct angle. And like I said, that's the angle from the horizontal, just like I drew above. So not only is force applied in the x that equation, force applied in the y also is the same equation. And that's force applied times sine theta. And that's the same for up and downward forces. So we talked about this in our inclined plane notes, but let's talk about it here. What's going to happen to our force applied in the x and our force applied in the y when we change these angles? Well, we said before that cosine of theta has a value from 0 to 90. And at 0 degrees is when it's at its maximum, and 90 is when it's at its minimum. Same thing with sine of theta. Sine of theta has a value from 0 to 90 degrees that we're concerned about. And at 0 degrees, it's at a minimum. And at 90 degrees, it's at a maximum. So that means that the force applied in the x direction will be at a maximum when our angle is the smallest. So this tells us that as theta increases, so as the angle gets bigger that we're pulling at, so if we're pulling from an angle that looks like this, and then we start pulling at an angle that looks like this, our force applied in the x direction will decrease. And our force applied in the y direction will increase. On the flip side, as theta decreases, and by decreases we mean as theta goes from an angle like this to an angle like this, so as theta decreases, meaning that it approaches 0 degrees, and theta increasing, meaning that it approaches 90 degrees, our force applied in the x direction will increase, and our force applied in the y direction will decrease. So these are really important concepts to understand because it can help us conceptually understand what's happening with angled applied forces. So last part is bringing all this information back together. So we said that an upward applied force will give us force gravity equals force normal plus force applied times sine theta. Well, if I want to know just how that impacts force normal, I'm going to subtract the force applied over. And I'm going to find out that for an upward force, force normal is going to be equal to force gravity minus force applied times sine theta. And for a downward force, we knew that force normal was equal to force gravity plus force applied times sine theta. We just set up here, though, that as this theta increases, so as our applied force becomes more and more vertical or closer to 90 degrees, force applied in the y direction is going to get bigger. So what does that tell us? Well, that tells us that as theta is increasing, if force applied in the y direction is getting bigger and bigger and bigger, force normal is going to get smaller. And if we look over here for the downward force, we're going to notice the opposite thing is going to happen. That as theta increases, so as our applied force is becoming more and more vertical, our force normal is going to get bigger and bigger and bigger. We are pushing down on our object, so the normal force has to be getting bigger to counteract that downward force. And then obviously if we just look at it the other way, so as theta decreases, so as our angle gets smaller and smaller and smaller, our force normal is going to get bigger and bigger and bigger. And again, from the downward force, it's going to be the opposite. As theta decreases, our force normal is going to decrease as well. So the last thing, I promise, so for an upward applied force, we're going to see that the angle and force normal are inversely related. As one increases, the other is going to decrease. And this makes sense because if we're pulling up at a bigger angle, that means that we're increasing the force applied in the y direction. So we're taking some of that pressure off of the surface. So the surface doesn't need to exert a big force on that object to keep it at rest. And for the downward force, we're going to see that the angle and the force normal are directly related. That as that angle increases, so as we push more and more vertically on that object, our force normal is going to have to increase because basically we're applying more and more force downward, meaning that the surface is going to have to work harder and harder to keep that box from moving down. All right, so for real this time, last thing. Let's imagine that you are trying to move a heavy object. Would it be easier to get in front and pull that object forward at an angle, or to get behind it and push it forward, applying a downward force at an angle? Well, the answer is that it's actually going to be easier to pull it forward at an angle. So go ahead and get in front of that object and pull it forward. The reason being is that when you pull an object forward or upwards, you are lowering that normal force. Normal force is going to impact that friction force. So a smaller normal force means a smaller friction force. Less friction means it will be easier to move that object. So when you guys finally move out of your parents' house, if that's going to college or something else after high school, just remember that when you are moving objects, it's going to be a lot easier to pull those objects than it would be to go behind those objects and push them. Pulling is better than pushing.